right, so we're going to go over photoelectron spectroscopy first. That'll fit through session 1. I'm going to try to run it for 45 minutes. Session 2 might start with periodicity and quantum theory, or a little bit in this one. I have a bunch of students behind me back here that are watching this already because we're having an AP review session on a fun 7:30 a.m. morning when our freshmen are taking a state test. So I'm just going to let them say, "Hey, YouTube." But they don't want to say anything. No, they'll laugh. So I want you to know they're there. And they might ask questions, okay? So let's go. So I'm going to go over photoelectron spectroscopy. It's called PES. So here is what it is. It was added to the AP exam in 2014. And last year, the AP test writers put an FRQ that was photoelectron spectroscopy. And supposedly it was on the multiple choice. So let's go over what it is. So what happens, I'm just going to pick an easy atom. I even have some notes I got to look at. We're going to use neon. So I'm just going to draw that little circle, and I'm going to call that neon. I'm not going to worry about all the orbitals yet. Energy levels, I'm just going to worry about the size of the atom getting bigger or smaller as electrons are either added or removed, okay? So with photoelectron spectroscopy, you send in photons. So it goes back to Planck's constant times frequency, and it's sometimes called incident energy, okay? So energy goes in, that's the simplest thing you need to know. So energy goes in, and then what happens is possibly this neon ejects an electron, and neon normally wouldn't want to do this, okay, and becomes a positive ion, a cation. So I might even ask these students questions, but I don't know if they'll answer. So it's a cation. I'm going to see how much they know. So we're going to write the electron configuration for both of these, okay? And we've never really said that neon can turn into a cation. There's a reason why I'm picking this one. So what would be the configuration? I'll just see if they can do it loudly without me telling them. So what's neon's configuration? 1s2, I heard it. 2s2.
2p6.
Oh, 2p6, okay? So those are the electron placement. We will go over quantum theory after this and periodicity to tie it together. So what would happen if it turned into a neon plus and an electron is ejected from the atom?
2p.
You end up with a 2p5. Good. So 1s2, 2s2, 2p5. Now, the other thing that happens is some kinetic energy was also released, okay? So it's a little bit of physics, just going to cover a tiny bit with it. So you've got your atom. This is a noble gas, which normally does not want to, or not, I shouldn't say want to. Energetically, it's not an atom that would have the easiest time losing an electron. I'm trying to say it simple. So keep in mind, these photons typically are really high energy, and a lot of times they're X-rays. And I like using neon because neon, you'd have to put a ton of energy in for those electrons to be able to be pulled off. So sometimes it's UV, but in this case, you'd have to put in X-rays, okay? So the next thing that happens is you can remove any electron, okay? So what we're going to do is say, well, what if it removed one of these two S's, okay? So you send in energy, and what happened is if, I'm just going to underline, what if we want to have one of the two S electrons be removed? It's still going to turn into neon plus, still going to have an electron ejected. It's going to be 1s2, 2s1, 2p6. We're going to take one from the 2s, okay? Think about back to quantum theory. Is that a lower energy orbital or a higher energy orbital, okay? Closer, sort of, not really closer, I shouldn't say closer, but more tightly held by the nucleus. What they found was the amount of energy that was released was less. So the amount of kinetic energy that they could calculate was lower. Slide this in, make sure we got some borderlines I can't go past here. Move this AP over. So then they did it again, okay? And now how did they do this? Let's not worry about that, okay? They did this again and said, okay, well, what if we try to remove one of those? Okay, so it's still going to be neon plus, it's going to be 1s1, 2s2, 2p6 plus an electron. And it was only a small amount of energy, kinetic energy, that was released, okay? So here's the math. So that's what happened. So they found that they put in, I got to look at the numbers, because I watched a video of somebody else helping me explain this to you. That's the amount of electron volt energy that was put in, okay? Then these kinetic energies that were released, I have them written down because there's no way I remember these numbers. This one was 1,232 electron volts. This one was 1,206 electron volts, and this one was 384 electron volts, okay? So here's the formula that you can use, is that the energy that's going in, let's just call it that, it's really got a fancier name, but for us in AP Chem, we don't really have to worry about that, is equal to the ionization energy, which is also sometimes called the binding energy. That's the energy of the electrons sort of being bound to the nucleus of the atom. And then it's minus the kinetic energy that's given off. So this is a formula that's not going to be on the AP Chem exam. Of course not. But it helps explain photoelectron spectroscopy. All right. So what you'll do then is if you want to find this ionization energy, you'll take this energy that you're putting in and you'll subtract it from the kinetic energy, and you'll get the amount of this binding energy of an electron. So that's the moneymaker. That's what the AP test wants to know about, okay, is that binding energy or the ionization energy, which is a periodic pattern, which will go to periodicity also, okay? So this ionization energy, you just do a little bit of math, okay? So I think I can fit it over here. Yep, there's plenty of room. So these are the numbers that I got. So for the first ionization energy for taking in a 2p electron, it doesn't matter if it's an X, Y, Z, going in all the different three-dimensional directions. I got that it's 22 electron volts. So what I did was I took this 1,000, let me just do a quick little math problem. I took the 1,254 electron volts and I subtracted it from the excess energy that came off. So that's all the energy that wasn't needed to eject the electron. Does that make sense? I'm kind of looking at my own students. I don't know if it makes sense to you people, but makes sense to you guys? Okay, so that's the extra electron. Nathan's smiling at me. Thank you, Nathan, for the encouragement. Then ionization energy for the 2s electron was 48. I'm trying to keep this short. The person I watch, this video is like 20-some minutes long. I don't want this to be that long. This one was 870 electron volts. Okay, so what this is showing you is that we have proof that the closer you are to, as an electron, to the nucleus, okay? So if you're talking about, now I'll kind of draw it. If you're talking about a neon, how many protons would there be in, I'm asking easy questions. How many protons would there be in the nucleus? Neon, right?
Yeah.
10, right? So how many electrons total would there be on the outside of that atom? We're going to do a little bit of quantum theory right now. In a neutral atom, yeah. So at the start. 10, right? So the first one we would say, is an energy level 1. We'll say that maybe that goes out about this far. And those are those 1s electrons, okay? Then you would say I have energy level 2. Let's say that that's all the way up to here, okay? Remember, these are fuzzy borders because we only know where the electrons are 90% of the time. So you don't want to say that you're sure. They could kind of be all a little farther. These would be your 2s electrons. Okay, and then there are p orbitals. Remember those? So you have one kind of going like that, and there are what are called nodes or dead regions, but we're not going to worry about that. And this one's coming out at you, and then this one's going back and forth. Okay, so you've got these 10 electrons. What this proves, okay, so what in the world are they trying to get at? Why is this on the AP Chem test now? What they're saying is that there's proof using this type of spectroscopy that the electrons that are in these 1s electrons here are being much more tightly held, and we have electron volts to prove it. How does that feel in terms of that makes sense? Like we have mathematical proof this is happening, right? And then these two are out at a second energy level. They're different, but we have proof that an S is more tightly bound than the binding energy than a P. We have proof of that because it all goes back to here, right? 1s, 2s, 2p. And then, 3s. Does that make sense? And then 3p. And then things get a little tricky because what happens after the 3p? We should go to that d orbital, but we have proof. So we could use this to prove this, that it goes to not the 3d, goes to 4s when it's filling, okay? Then it goes back to the 3d, okay? 3, 4, 5. that make sense? So this is the proof of that, okay? So at first when they put it on the AP test, I was like, oh, come on. But it does make sense. It's a good way to tie it all back together. All the quantum theory you learned, all the electron configurations, ionization energy, all that stuff comes back, and we have proof of it. Because usually AP students are mathematical, you know, and they want to see that there is something out there that proves that this is really true, not just that people are thinking it's true. Okay, so what does it look like? So I have to erase this, okay? So I'm going to give you a second here. This is not what it's going to look like on the actual, like, printout. So the spectroscopy machine, per se, prints out a graph, okay? So this is like what's happening behind the scenes. So I'm going to leave kind of those numbers there. And really, this equation, I'm going to erase things kind of in order. This equation is not really necessary. It's just kind of nice to know. Will you have to know that X-rays are used? Not really. Will you have to worry that they're called photons? No. The big thing is that you know that electrons are going in towards an atom, and we're trying to make electrons come off. Okay, so, and then the only thing is that there's excess energy that we subtract, and then that shows us how tightly bound those electrons are. Okay, so let's keep going. What would it look like then on a what's called a photoelectron spectroscopy, like kind of like a printout, I'm going to say. So there's a couple things I've seen. There's a couple versions, okay? So the most common version looks like this. You have number of electrons over here on the y-axis. Like that's the most common one. And then I'm going to switch to black in a second here so we can see this better. And then you'll have binding energy here. Binding energy is sort of, you know, code name for ionization energy. Because we really haven't heard binding energy until probably now. We always say ionization energy. So then the other thing that you'll see, and you gotta just be ready to roll with it. Sometimes the larger number for binding energy is over here, and a kind of a small number, like even 0.1, will be way over there. Okay. There's also a possibility that it's normal. They put the 1,000 over here, and they put the low end over here. It doesn't matter, just stay focused as to what it means, okay? So what does it mean? So for this one, here's what it would look like. So we have 870 electron volts would be over here, and there'll be this like little peak, and I'll draw another version of it, but I'll just draw it as like that, okay? There'll be a little peak. Now that's not quite accurate, but it's okay. And then they may even label like this was the 870 electron volts. And then it'll be like this tall, okay? Or maybe it'll be even a little bit shorter than that. Then way kind of over here, there'll be a big gap. And then you'll have, this one will also be the same height because it's the number of electrons. So let's go back to, again, that this would have 1s2, 2s2, Hund's rule applied first, and then 2p6, okay? And if we wanted to remove every electron, and we could because we're putting in X-rays. So normally this would be a lot of energy, so we're going to remove every electron. If you did do that, this peak, if you took all the 2p's, would be, you know, this was 2 electrons, then that would be 4, and this would be 6. Does that make sense? So the height of that is showing you that these are the 1s2 electrons that are tightly bound to the nucleus. These are the 2s2 electrons, and then this height shows you that these are the 2p6, all 6 of them, okay? The other way you're going to see this, and let me draw it, and you have some pictures right here, okay? So I'm just going to kind of hold up, like, probably this one, okay? So I'm just going to show this picture right here, okay? So sometimes they're not like a straight line. They actually look like a little, I don't want to say a heartbeat, but they actually kind of come up like this. So they'll be like, I have a student who has the hiccups, and she's probably like, please stop hiccuping. So they actually kind of peek out like that. And then, you know, this one would be like that. Okay, so they look like that. So just don't be shocked if you see a graph. Let me go over here. If you see something that looks like that, it's okay. Okay, and then on here is a good example of this printout that I took off the internet. I don't even know who to give credit to because it doesn't have where I got it from. So whoever you are, thank you very much. But here, right there, you can see that the binding energy starts at 0 and goes up. The other thing they'll do is they'll tear it upwards like that. So they won't go left, right, because it would be super long. So they'll go this way. So what I want us to do is look at this one right here. It says looking at the spectrum for scandium. It even tells you, okay? So it says scandium right on there. So let's look at why is that scandium, okay? Let's try to label each of the peaks. So I'm going to try to draw a version of it right here as best as I can. My students are just kind of looking at that picture right now. So then it might say relative number of electrons. That's another way you can label the axes, relative number of electrons. And then it starts at 0 and goes to 10. And then all of a sudden they have this other one kind of here, like this. And then that goes from 10 to 100. This is just another way that this can happen. So you just got to be ready for any one of these types showing up. And then they have 100 to 500. The other thing that they might do, okay, is they might have it so that it is kind of long. But what they'll do, and you've seen this, I would hope, in math, they'll go like this. There'll be these huge breaks. And they're just trying to not make it have the whole axis. So they would go, 0 to 10, and then maybe they'd have a break, and then they would go, 100 to whatever. So they might do that also, okay? But let's stick with this one. I've seen this show up plenty of times. So they have, like right here is the lowest. So they have this little peak right here. And then they have another little one right next to it. And about here, there's this size. And then there's another one here. It's actually very tricky to draw. Mine will probably not be very well to scale. And then it's got kind of a big peak here. And then this source actually put numbers on top of these already. Okay. So this source actually said 2, 1, 6, 2, 6, 2, 2. And I won't worry about the electron volts. The other thing this can be is besides electron volts, don't be shocked if instead of that, it's megajoules per mole. So just be ready for any of these changes, okay? They might not use electron volts. They might use megajoules per mole, which I think is more chemistry related. And then it could start with 0 on the left and get larger on the right, or they could have an opposite. Okay, so let's just quick shout out what we know scandium's electron configuration to be. The whole thing, no shortcuts, no noble gas as a core, okay? So what is it? Let's see if they will answer question. So scandium, I'll write the word.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1.
Okay, 1s2, 2s2, 2p6, 3s2, and then 3p6, right?
4s2, 3d1.
4s2, 3d1. Okay, so there's our configuration. Now somehow this photoelectron spectroscopy graph is going to explain why those electrons are bound the way they're bound, okay? So if you look, where are the most tightly bound electrons on this graph? So they would have the highest binding energy, the highest ionization energy. I'm off the screen, I'll come back in here, over here. Yeah, they are up here, okay? So for this graph, I'm gonna see if I can actually slide this over. My screen actually has more space here. This is gonna be our 4s2, okay? Right? It's going to be the testing you. 1s2, right? Okay. And then, do we have proof of this? Let's go to the other end. So this is going to be our 1s2 here. So let's just go to the other end of the spectrum, the opposite side. So then, what's this one? This is our 4s2 and 3d1. Now, this is where I will totally not fault a student if they have a hard time doing this next step, okay? Because of knowing this, it causes another problem. What's a common ion of scandium? Okay, so this is scandium, like you guys asked me at the very beginning. This has a 0 oxidation state. It has neutral proton electron count. They're the same number. What's a common ion for scandium? Plus, it's a transition metal. The 2+, yeah. So now be careful, okay? which electrons are removed when you go from scandium with a 0 oxidation state to a 2+ charge or a 2+ oxidation state? Yeah, be careful, the 4s2. Now, on this graph, you could see some people kind of saying, well, the 3D is just a smidgen higher. But what does the 4s have that the 3D doesn't? Go back to that. Energy level 1, 2, 3. It's a horrible picture of an atom, but I'll get rid of it because now it's on YouTube Live forever. That's embarrassing. So what does the 4s have? It's farther out, right? Okay, so be careful. The 4s is the one that's removed. So if somebody said, well, give me the full configuration of this one, it'd be 2s2, 2p6. Now, most of the time they wouldn't ask for the full. They would want the short one. But let's just do this first. So that's scandium, ion, 2+ ion. How would we shorten all that? Yeah, so we could take all this and put argon. Okay, I'm going to put it up here. So argon and then 3d1. Are we okay with that? So it covers a lot of things in one fell swoop that goes back to configurations. It goes back to, again, you have some proof that, yes, these two are pretty close in binding energy, but the 4s is farther out. So that's the valence electrons. Be careful also with valence, that this really only has 2 valence. Now, this is a trick question, kind of, but not really. I've not seen the AP test writers ask this, but I've seen it on our academic team competition in our little local area here in the Greater Green Bay. I've had them say, well, how many valence does this have? So go back to here. Now, what's valence in the scandium ion? This is a tricky question. Yeah, all of that. So you're actually going to say it as a valence of? 9. And it feels really weird to say valence of 9, okay? Because usually it stops at what number? 8. So they're testing you. I have seen that show up. No, not in the AP test, okay? But this for sure you need to know that those are the valence electrons, okay? All right. So what I'm going to have us do is you can kind of make a summary. I'm going to try to write a really big table right around here. So if you were to see one of these photoelectron spectroscopy graphs, don't panic. All they're trying to do is the height of the peak is the number of electrons, and they'll proportion it pretty close. So if this is 2, then that would have been 4, and this would have been 6, okay? And they might not label it, okay, that's fine. Then be careful that you always remember that wherever the highest peak or the highest binding energy peak is, those are going to be your first electrons in the first energy level. And then just go backwards from there. So start from that aspect, okay? So if you were to see one of these graphs, this is kind of the big theme, and then we're done with photoelectron spectroscopy. We can do a couple of sample problems if we want. So I'm going to try to draw this really big. And I found this again on another site. So if you see one of these graphs, okay, don't be worried if they end up breaking it. Okay, that can happen. Don't be worried if they end up stacking them. That can happen, okay? Down here, they're probably going to call it binding energy or just energy. So put all the choices, binding energy, energy. I highly doubt that they'll call it ionization energy. I've also seen it labeled as change in, I think it was U. Literally, I'm not joking, the letter U, okay? Which probably relates somehow again to physics. I actually am not sure what that one's all about. So just don't panic. Sometimes binding energy, people do BE. And then it could have the units of electron volts, or it could have the units of megajoules per mole. Don't panic. Same thing. It's just the energy it took to take that electron out of the atom. And we were going to take all of them. That's what's crazy about this, in my opinion, is you're taking every single electron out of these atoms with this high energy that you're adding. And then over here, the common one is number of electrons, but they might add the word relative number. There was one more axis, but I don't think you're going to see this. I saw somebody label this as signal intensity. I don't think we're going to have that on the AP test, but you could have that. Okay. So to me, that's the summary. The other summary too is if this is the this is the large end, I'm just going to put 1,000, and this is the low end. Remember that these electrons down here are, kind of put a little summary for yourself. These have the highest, that binding energy. that means they are they're the hardest to remove. They are core, we might call them core electrons. And then you can say that, they're the hardest to remove. You could even bring in here that, Coulombic force is high with these. They're being held tightly to the nucleus. And then if they're way over here, that's completely the opposite. These are the low binding energy. And then typically I like just to say that, these are where your valence are at. So when they get to chemical bonding, we're going to tie it into Vesper theory at some point. These are the electrons that are involved in the Vesper theory bonding that we're going to do too. Okay. What else? And then don't forget that the height. So if you have a peak that's this high, and you have another peak, that's maybe only this high. That I'm trying to do it pretty good here. Maybe one. Yeah, it's a little bit too tall. Like that. This could be 6 electrons and this could be 2. So the height of the peak is going to be how many electrons are in that type of orbital. Alrighty, we did pretty good. I think that was about a 20-minute spiel. I'm going to keep going for about another 20 more minutes. So I have no idea if anybody's watching. Nobody's chatting. That's fine. But if you watch it later. So we're going to go from this to quantum theory. And then I'll try to tie in periodicity at the same time. So I'm just going to ask my students, though, if they have any questions before I go. So these are the names of the students. And this is actually just for me to remember this forever. One, I actually have a student teacher way in the back. You can't see, he's hiding. His name is Mr. Carlson. So he's listening to all of this. And then I have Josh, and I have Aaron, and Eli, and Michelle, and Emma, and Dane, and Troy, and Nathan, and Richmond, and Kylie, and Abby, and Megan, and Ashley. I'm not telling you their last name, so it's a secret, okay? But they're in here, so they came on morning. So I'm gonna ask them a question. Do you have any questions? Crickets. Crickets. Does it make that much sense? Or did I just baffle you with, numbers? Okay, we are not gonna be scared of this photoelectron spectroscopy. So I'm just gonna hold up the AP question. Okay, it's on the internet, so I'm not showing you anything you can't find yourself. So here was the AP question last year, and I had students wigging out, coming back, freaking out, okay? So there it was, okay? I'll kind of cover up the answers. I think the student got it right, though. Is it nitrogen? Okay, so this is one of my students. I won't say who either. And then what was the next question? Radioactive isotope decay, half-life 10 minutes. What in the world does that mean? You know what kind of reaction order? Because all radioactive decay is always what order? First order, okay? So you go find the equation. So what was the K value? This person has 6.93 to the negative 2. I think that was right. And then what was the last thing? If 64 atoms radioactively decay, what's the expected half-life, right? What do you guys think it was? 60 minutes, I think. I think I grabbed a 4 out of 4 right here. Look at that. Okay, so I don't know who this is. I could probably look at the name last year, but I think those are the right answers. So that's what it looked like. It's not that bad. And then they had it the way I have it here. What did they use for units? Megajoules per mole. And they had binding energy, and then they had number of electrons. So they stuck with some nice, easy labeling. Honestly, if you knew what you're doing in this question, easy 4 points, I think. Okay, as long as you know kinetics of radioactive decay is first order, you got your equations, you go get them, off you go, okay? So I got lucky, I grabbed a good one. I'm gonna keep this one, I think. Maybe they've got, I had some 5s, so we'll be all right. Okay, let's keep going to something else. Are you sure you're good? Looking around at faces. Okay, now if they don't put this on the test, they need to put it on the test. It's all over last year's test. And it is important. My student teacher, did you do any photoelectron spectroscopy with an actual machine? I never did an instrumental analysis.
No, we didn't. We
just talked about it, yeah. If you want to donate one, we'll take one here. Okay, I'll give you the address. Okay, here we go. So let's move on. Another major topic, in my opinion, is periodicity. Periodicity. Okay, hope I spelled that right. So what are the periodic patterns? Like, what are they? Well, obviously, ionization energy, right? That's one of them. I'm going to try to save space, so I'm just going to do IE. That's not it. There's a lot of periodic patterns on the periodic table. That's why it's probably called periodic table. I'll let them answer. Any other ones? Lattice energy, we could possibly. That's a tricky one, but I bet you we probably could.
Atomic radius.
Atomic radius, so I'm just going to put AR. That's the big dog on the block. You got to know that one. And then usually there's 2 more. But you could do 3 more, though. But 2 more for sure. Electronegativity, when we get to sharing electrons, that has to do with the pulling that affects polarity. What else? Electron affinity. A lot of people skip this one. I think it's important. The only thing that's kind of weird about electron affinity is that it's a negative value. Okay, so when it's a negative value, that just means look at the numerical amount. The negative just means it's exothermic. Okay, but the larger the number, the more exothermic it is. Okay, so let's just kind of build. I'm not going to build the table. I'm just going to draw, a box sort of that looks a little bit like a periodic table. Don't judge my periodic table. I'm drawing on the fly here. Oh, that looks bad. Who cares? Moving on. You gotta live with what you do live. Okay, so if you're perfectionistic, this is not a good thing to do. And I am. Okay, so where do they go? So let's just draw atoms with spheres. Okay, so what about atomic radius? That's the most important. I'm gonna back up for a second.
Largest and lower levels.
Yes, yes. What largest are on the lower left, so let's kind of go crazier. Large atoms down here. Okay. They're large because the easiest thing is they have a lot of energy levels, but there is also something about their proton count that makes them also have the loose hold of those electrons. Okay, so then up here they get smaller. So let's just say we've got, let's go like that. Okay. This is the tricky one. As they go this way, they actually end up getting smaller. Okay. So the big thing, what you want to say is when you're going this direction from here to here. So if you're going across the table and you're going this way, okay? I'm just going to try to draw an arrow. Over here, you'd say energy level 1, 2, 3, 4, 5, 6, 7, right? I'm working on an 8th row. So what's that number for? That's the energy level, okay? So what you're going to have to say when you talk about this, you want to very clearly give succinct answers, okay? You saw this person right here, whoever this was, they didn't have a lot of work, and they probably got 4 points, okay? Succinct answers get you points. Long answers might, okay? But get to the point. So you have the same energy level. Say that, okay? So you have electrons being added, okay? Because let's say who this is. This is lithium, right? And then what element is sitting way over here, way on the other cross? Don't worry about the noble gases. We don't want to talk about those right now. This is fluorine, right? They have the same energy level. What you can even do is say this is 1s2, 2s1, right? Okay. What's fluorine? 1s2, 2s2, 2p6. This is correct? I have a couple people out there that if I say something wrong, they're going to give me a look of like, yeah, that's right. Oh, 2p5. See, that's where I need people. 2p5. Okay. So electrons are all in energy level 2. Okay. But there's more of them. Okay. That's the tricky part, is there are more electrons over here. So what you need to talk about is that these both have the same energy level, but what's happening with that proton count in the center? And you can use fancy words. You can use effective nuclear charge. I mean, there's words that the AP test likes, but they can't fault you for correct just proof also, okay? So what would you say? Well, this has how many protons in the nucleus? Lithium has? 3, okay? So if this has 3 protons in the nucleus and this one has 9, there's a higher proton count that is able to pull on those electrons in that same energy level to pull them in. So it has fancy names, and you can use that. I think even in the rubric I printed for you, you can find how would you explain it if you want to use the fancy terms. But they're really looking for same energy level, more protons that are positive, pulling on those same distance, and they're going to get drawn into the center. Okay.
So you're gaining more electrons as you go from left to right?
Yep.
So you also have more electron repulsion?
Yes. So
How do
let's
you-
list the things, because there are going to be more electron repulsions going on. And that's sometimes what Eli's saying is sometimes the answer they're looking for. Last year they wanted more electron repulsions for an answer to something. Okay.
So then this is saying that
This is
the
more.
attraction between electrons and photons is stronger than repulsion?
Yes.
So do you have to say anything?
You
prove
probably wouldn't
that?
have to say that, but if you wanted to, just make sure you're very clear that the electron repulsion, because you are gaining more, is must not be a big deal compared to the fact that that proton count is really where it's at. Let's make sure we write down Coulomb's law. So I'm going to have Eli's actually help me out. So its force is proportional to, and they talk about Coulomb. Make sure I spell it right too. So Coulomb's law. If you look at that rubric I gave you guys, again, that was printed from the AP site. Coulombic force or Coulomb's law is a lot of places. It's almost like if you wanted to find it, you could count, I don't know, 10, 20 times. I have no idea how many times, but it's a lot. So did I spell that one right? I'm having Eli kind of check on the internet here.
Yeah.
And then what is it? I think it's charge.
No U.
Oh, no U. So it's just COLOMB. I feel like there was supposed to be a U.
CO2.
Oh, it's COU. See, I can't spell at all. This is called spelling in chemistry. COU. I found it too on here. COULOMB. That looks crazy. Okay. And they basically say force is proportional to what? So I found it actually on this while he maybe looks. I just found it. Oh, right there. So actually right there. But you can't see it because it's too small. Right in the first one it says periodicity. Big idea number 1. Uses the shell structure of the atom to determine electron configurations and relates these to the structure of the periodic table. Are we doing that right now? This is exactly what we're doing. Communicates the form and basic consequences, big words, right, Emma? Of Coulomb's law. Recounts the shape of the s and p orbitals. So we hit, didn't I actually do all of that in the 30 minutes I've been blabbering? I think so. Okay, so what is it though? Let's get the law. I think some of you in here are kind of mathy people. What is it? Did you find it, Eli? I think it's Q1.
K plus Q1 plus Q2 over D squared.
Yeah, and then there's a constant. Is it a big K or little k?
Little K.
Little k. No, we got to be careful. That's not rate constant K. You know, we'll just call it a constant. Okay, there's big K, which is equilibrium. Little k, which is a rate constant, rating. Just this is another one. It's not related probably. Okay. And then D, I think, is the D squared.
D squared.
It's like the distance. A lot of times it's the radius of the atom. Okay. So all it's trying to tell you is that if charge is larger, force is, keep it simple, people. Force is larger. If the distance between my atoms or my nuclei where the attractions are larger, then the force is smaller. If the distance is smaller in the denominator, the force goes, I feel like Star Wars, the force is strong, it goes higher, okay? So you can use that equation. I see that a lot, people using that equation to explain this stuff, okay? Let's just keep going. I really like this. I printed this for my students, okay? So it says, portrays the properties of atoms and or binary compounds, recounting periodic trends, okay, blah, blah, blah. So I think, I have no idea, but I think that would be a 3, 4, and 5 is my guess. So kind of for my students that are looking at this document, I'm thinking they're saying that's a 3, that's a 4, that's a 5. So with periodicity, if you want to be 5, you got to do all 3 of these. And then make sure you read the big chunk that's sitting over there. What was your question, Eli?
This said that K plus Q1 plus Q2.
K plus?
Didn't write.
Oh, where is it?
K plus Q1 plus Q2.
Like this?
No, you had it.
I had it right.
It's all over D squared.
Okay.
Plus.
Oh, I know what you're saying.
It just might look like.
And a lot of times they don't even put that in there. That's why it's confusing me. So there is a constant that we have to put in there. We add it. Sorry about that. The key here, though, picking on Josh. Today's supposed to be all about Josh. Josh came from a different school, and so he has a lot of holes we call in his little pirate ship boat for pirates. But he's going to fill them. He's a mathematical stoichiometry master, though. Good at that. Okay, so cool. Are we good? So electron repulsions is kind of a key word, although like Eli said, that's not a good time to say that one right now, okay? There's really 3 of them, I think. This one is sort of that effective nuclear charge, which is the charge of the protons. If you don't want to say that, you can just say this has 9 protons, this has 3. The energy level staying the same. there is a higher pull due to Coulombic force. And you're probably going to be good to go. Got it, Megan? You'll be fine. Okay? All right, another one is going to be the other direction. This is the easy one. They almost never ask us this. Why is it larger as you go to the bottom? This is the easy one. This is the moneymaker one, but they don't ask you this. This is an easy answer. More energy levels, right? So it'd be nice if you could say more or less, more or less energy levels, EL. Okay? That makes it larger or it makes it smaller. Okay, and that's going to affect these electrons. Okay, one more. The last one, it has to do with the, effective nuclear charge. And then some books will call it ZEFF, okay? That has been a big controversy as when you can use that one and when you can't. So for mine, I always say stick to the facts. Put down the configurations, put down the proton count, say what it means, get in, get out, go find some more points, okay? If you want to use the correct wording, it's nice if you can, but the facts are the facts are the facts, Jack. That's the way it should go. Okay? That's the way it's supposed to be. Math it if you can. That's sort of the way to math a question like this. All right, next, ionization energy, high or low. Okay, so we've got, let me do this. We've got our atoms being larger here, because I'm going to erase this arrow here, okay? This one. And they get larger as we go this way, okay? So most of the time in most books, you're going to see these arrows. So that's going to be our atomic radius arrow, where they're larger, okay? That one. All right, let's just switch colors. So that's the main one. That's the big dog on the block. How about ionization energy? Which way does it go? So it's just going to be ionization energy, i.e., which way should the arrow be for the highest ionization energy?
Opposite direction.
The opposite direction. Okay, that's going to be the key here. Opposite direction, people. Get rid of these here. Get out of here. This way. We're almost to the end. We're going to go about 5 more minutes. So that would go this way, okay? So the key here is your small size atoms, we have the tightest hole. Now, do we just learn something at the very beginning of this to prove that? Because they're closer to the nucleus, they have that higher electron volts. This is where that photoelectron spectroscopy makes more sense. And some people are saying, well, why don't you just teach it in first-year chem? I don't think the first-year chem students are ready for it. I think it's good to do now and be like, look, we have something to prove it, okay? What else? Let's do another color. That's ionization energy. I'm actually going to get rid of the word periodicity here, too. Think about the next 2 patterns. And we already did a lot of ionization energy, so I'm not going to define that one. We just did that. That's photoelectron spectroscopy, moving electrons from a gaseous atom. I didn't say that, but it should be a gaseous atom. It's endothermic, obviously. What's another one? Let's see if that's on the screen. Oh, yeah, we'll be good. So blue. I'm going to put these back here, our little markers. Let's do another one. We've got, let's do electron affinity next. Oh, sweet. So electron affinity, if you don't know what that is, that fits on the screen. Looks good, red. Electron affinity is the energy to add an electron to a gaseous atom, and typically it's exothermic, okay? So you usually have a negative value. But which ones have the larger negative values? Yeah, it's the same. You're going to see something really easy here. Some students are so baffled by this. I kind of go, but why? I don't know why. Or maybe it's just because it's new. So that's the same. So this fluorine has the most, or one of the more energetic, I should say the most, one of the more energetic, because there are some flaws that happen here. We'll talk about the exceptions probably won't even put it in this video, but there are exceptions sometimes too, depending on how they're paired. But typically, up here, these have the highest exothermic release of energy when their electron is added. So these tend to make what? So again, how does this relate to where we're going next with bonding? So over here, this whole section here tends to make what kind of ions? Because they can gain electrons, give up more. Yeah, these are going to be our anions. Or if they're not going to be anions, they can also share those electrons and do a covalent bond. That's an option too. And what about the bulk of the whole table? That's green. All of these guys and gals in this area here. That holds sort of most of that chunk. Those are going to be cations. Now, if they can't be a cation, They have one other option. Can they bond with each other? Sure. And they can do metallic bonding, which has the delocalized electrons. Okay. So keep delocalized electrons. Cations would mean that they lose an electron. Anions would mean that they gain electrons. This is where we'll start with our second video. And maybe some quantum theory, or the third video might be this. I haven't decided yet. But you can lose electrons. You can just kind of delocalize your electrons. These are all the types of chemical bonding. You could gain or you could share. So we've got ionic bonding. Like I'm going to circle ionic bonding in pink. So this and this would make an ionic bond. Okay. And then lime green. Let's just say that that's covalent bonding. So that's going to be our covalent bonding. And then last but not least, if we're just going to delocalize them, let's use orange. We would have metallic bonding. And then that doesn't include the covalent network. That's a whole separate story. Okay. Last trend. We're almost done. I'm going to use this light blue color here. Maybe not. Yeah, we'll use it. It'll be fine. So then what about one more? Electronegativity, right? Electronegativity is defined as, so this is electronegativity. Just going to put electroneg. The red one was ionization, or no, electron affinity. Okay, got it up there. And then electronegativity, which way does it go? Same way. Because again, smaller atoms, when they're going to share, are going to pull on the electrons in that chemical bond more tightly to themselves. That's going to create some, if there's a big enough difference, you're going to create some polar covalent bonds. If the difference is so great, there are people who say there really aren't any ionic bonds. The polarity difference between their electronegativity is just so great that we call it ionic then. But really it's an extremely polar bond where there has been an exchange, they believe, of electrons, okay? That there's no sharing anymore. The difference has been so great that you just end up losing and gaining electrons, okay? All right, so that's it for the first one. So periodicity we covered, I'm saying we're good. We could probably add some exceptions. I think with my students, I'll go over the exceptions. I'm not putting them on the video. If you want to know, you'll have to look them up. But yeah, there are going to be some exceptions in electronegativity. And there are even some in ionization energy when you're starting to pair, when you do Pauli's pairing of electrons up and down. Sometimes the electron is a little harder to remove or easier to remove than you would have predicted based on these patterns. So look in your book for the exceptions, okay? We are going to have a snack and we're going to take a break. And the second video, I think we'll do either quantum theory or Vesper theory, but probably quantum theory and then maybe a little bit of Vesper theory. And then the last one will definitely be intramolecular forces and intermolecular forces at the end. That's it. Now let's see how long this takes to stream.